Variables are the currency of any C program. Without variables, we cannot do anything of value on a computer. Variables allow us to store information in memory so that it can be manipulated or communicated. The different places in memory where data resides are called objects. To access such an object, it must have a name, and such a named object is called a variable. The information we actually store inside an object is called a value. Of course, the machine itself typically has no idea how to interpret the information it contains, but the program certainly needs to know. For this reason, a variable has a specific type. And it's this type that constrains the use of that variable such that only operations appropriate to the type may be performed. Constants are slightly different between C and C++, and this can cause a bit of confusion if you come from a C++ background. C programmers tend to use macros, a pre-processing step provided by the compiler, to insert constant values into the source code. The trouble is that the preprocessor is by definition outside the language and thus knows nothing about your types. Now you can define a variable to be a constant in C, but it is not considered a compile time constant, and so you are still stuck using macros or literal values for this. Computers don't care about variable names, but we need those names so that we can refer to the underlying objects. We see those names in local variables, function parameters, and so on. Variable names consist of letters and digits, but must begin with a letter. The underscore character is also regarded as a letter in this context. But you should avoid beginning a variable name with an underscore, since libraries often use that convention as a sort of reserved namespace. Variable names are case-sensitive, with lowercase letters typically used for variable names and uppercase for constants. Like most languages, C reserves a few keywords, and these cannot be used as variable names. It's also a good idea to avoid C++ keywords to improve the portability of your code. Luckily, the compiler is great at catching these sorts of mistakes quickly and easily. C only has a few data types. Char for character, typically capable of storing only a single byte. Int for integer. Float for single precision floating point. And double for double precision floating point. There are variants of these such as short int and long int, as well as signed and unsigned versions. Although there are some constraints, it is up to the compiler and target hardware to define the size or how many bits of information each type represents. Obviously, the more bits, the larger the range of numbers, or the greater the precision of information that can be stored in a particular object. This can become problematic if your code assumes a certain bitness or size for a certain value. So C provides something called a typedef that lets you define your own type names. This is incredibly useful if you care at all about maintainable and portable code, as you can define types for, say, 32-bit unsigned integers and give it a clear name. Before you can use a variable, it must be declared somehow. A variable declaration combines a type with a name. This is distinct from a variable definition, which sets aside some memory for the object. Don't worry too much about this distinction just yet. It's just something to keep in mind for now. Often the declaration and definition are one and the same. You can also initialize variables when they are defined, giving them their initial value. You might notice that C code tends to avoid initialization more so than C++ code. The reason for this is that, unlike in C++, variables may only be declared immediately following the left brace of a compound statement, defined by curly brackets. The rationale is that it improves maintainability to explicitly assign values to variables close to the point where they are used. The declaration or definition of a variable comes down to storage and visibility. Where is it stored, and who can see its name and thus access its value? Variables declared within a function are the best kind. They are private to that function, so no other code has direct access to them. You can have variables with the same name in different functions and they will be completely distinct. These variables are sometimes called automatic variables because they come into being when the function is called and automatically disappear when the function returns. This also means that these variables must be initialized or assigned some value every time the function is called. They do not maintain their value. For the sake of efficiency, these variables aren't even given an initial value unless you yourself initialize them. The alternative is what is known as an external variable because it is external to any function. You might call these global variables if you come from a C++ background. Such a variable may be declared and defined separately. You may have its declaration in one source file, called a header file, that different source files can hash include in order to use the variable, and have its definition in exactly one source file to set aside the memory to contain its value. I tend to avoid doing this, however, as it can get quite messy as the different parts of your program become so tightly coupled through a series of shared or global variables. A variant of this is called a static variable, and they are very useful. A static variable is privately declared and defined for the exclusive use of the functions in a particular source file. It's basically a sweet spot between automatic, as in local function variables, and global or external variables. You might have a set of related functions that need to share some state, but that should not be directly shared with any other part of your program. That's what static variables are for. Another use of static is for local variables internally declared within a function. Unlike automatic variables that I mentioned before, the storage for internal static variables are retained across calls to a function, and their initialization happens the first time the function is called. I'll then add the standard main function and return value. In the previous demo, the main function printed a message. This time I'm going to use a separate function, which I'll call hello. For that to make sense, I need to provide a suitable definition for the hello function. I can now save and compile and run. And I'll add the standard main function and return value. I can now create variables local to this function inside the main function. These are called local variable definitions as they introduce the variable names and types as well as providing storage for them on the stack. Let me now go ahead and print out their values using printf. Here I'm using a new printf feature called format tags. The %d just tells the function to format subsequent parameters as decimal values. Printf provides a variety of format tags that you can use to format values in various ways. If I go ahead and save and compile this program, we might be in for a little surprise though. Well, it isn't such a big surprise in this case since the compiler warns us that the variables weren't assigned a value before being used. Still, the program will run, but the result is unpredictable. We can go ahead and initialize apples to some value and initialize oranges using the value of apples. Here I'm initializing the variables right at the point of definition, but I can go ahead and assign them values later on too. If we now compile and run, we should notice that apples and oranges have the expected values. Apples equals 4 and oranges equals 5. Apples set. And apples get. So we now have a global variable called data. This variable represents the shared storage for the two functions that get and set the apples value. Now if we update the main function to print the value of apples using this get function, we'll notice something different. Again, we'll compile and run to see what happens. And sure enough, the program prints 0, even though we never initialized the apples global variable. The global variable is initialized to 0 before the program's main function is called. Of course, the main function can still access the data variable directly. We could hide it by placing the apple-related functions in a separate source file. We now just need to update the program.c source file to include the declarations of the Apple-related functions, and the implementation is hidden from the compiler. I can now call the set function to indirectly write to the global variable, and the get function to read its value. So far, so good. If I go ahead and compile and save and then run it, I can see the expected value. Remember now that there is more than one source file, so I'd better name the resulting executable. But now, what if I needed to add another library to handle oranges? I can add similar functions to support oranges. Oranges set, oranges get. Great, now I can use apples and oranges together, right? Let's give it a try. Apples set to 5 and oranges set to 10. Let's print them both out so we can see. Oranges percent to D and oranges get. Now if I go and compile and run this, we might be in for a little surprise. fvprogram.exe to give it a name. Now we see apples equals 10 and oranges equals 10. As you can see, setting the oranges somehow also overwrote the apples value. This is another one of those differences between C and C++, which can get you into trouble if you're not careful. Using the C++ compiler to check the code helps to pinpoint the problem. You see, in C, a global variable is just a declaration unless it's initialized. In contrast, C++ assumes there are definitions and warns about the duplication. So one way to solve the problem is to always initialize global variables. That way the C compiler will pick up the duplicate variable name and warn you about it. But this is risky because you might forget to initialize one. Another option is to use different names, but that can become problematic as the program gets larger and more programmers work on it. Fortunately, C provides a solution to this problem, and one that works just as well in C++, and that is to use static global variables. Again, a static variable is privately declared and defined for the exclusive use of the functions in a particular source file. If I prefix each global variable with static, they will no longer collide, and the C compiler will provide distinct storage for each variable.